thank you. Thank you, Ben. Thank you for the introduction. Today, I will talk about some of our work on the security impacts of caches over ARM TrustZone. So the outline, first I will talk about what is the trusted execution environment, and one type of this solution, the ARM TrustZone, provide this on the mobile devices, such a trusted execution environment. So I will talk about two of our works. So one is called CacheKit. This actually is a rootkit which hide in the cache, so it can escape from this this checking the virus detection from this ARM TrustZone, the secure world. And also we'll talk about another CITM, catch in the middle attack. So this is about some attack against this isolated execution environment in the normal world. And then the summary. First, what is this TEE? Right? So you think about for our mobile device, when we process our payment or banking information, like your user password, so we need a trusted environment to protect those sensitive data, right? So even if you think about, oh, our Android OS is compromised, we still want to protect our sensitive data. So one example of this TE, you think about this, our SIM card. Actually, SIM card is just, you can think it's as one co-processor, right? Process everything inside this small card. So even if your this smartphone has been compromised, the information processed, those keys stored in this SIM card still are secure. So another requirement for this TE is nowadays we have this BYOD, right? Bring your own devices. So it's allow you to process both your personal data and business data, those applications on the same hardware. So there's concerns, right? What if you install your personal those applications, which may contain various vulnerability, compromise the whole device, and then it may compromise your business application. So there's a demanding, say for this Samsung, they propose this Knox. See, or on the same smartphone, we provide two isolated execution environment. So even if your normal OS is compromised, so those secure applications still can be protected. And another example is think about this cloud, right? For the cloud, how can we trust those cloud service provider? They won't just look into our sensitive data, right? So that's why we have this SGX. Intel proposed SGX to protect this customer's data. Say even if those hypervisor or OS cannot be trusted, we still can guarantee to protect the client's data or application. So the properties of the TE, they have this 5 features. First, we need to provide one isolated computing environment, called ICE. And also we need to have a secure storage on the disk. And also for the remote attestation is say, okay, if we install a client application on a smartphone, when we connect to the server, we need to verify, okay, our current, this client version can be trusted, has not been modified. And secure provisioning means we can establish a secure communication with the remote application. And this trusted path actually is, now we have two systems, right? One trusted system, one normal system on the same device. They need to have some interaction between these two paths. How we can guarantee those IOs, communication channel between these two environment. That's called a trusted path. You can think about this input, output into this TE. So now let's look at ARM TrustZone. This is one type of this TE. So ARM, the idea is they use some hardware features to separate this system into two domains. One is called the normal domain, another one is called the secure domain. So in the normal domain, you can think about like we can install our Android or those just Apple, this OS on this normal domain, and then regular applications on this environment. And then you can install your another secure OS in this secure domain, and then install and run your trusted applications. So this hardware, they can provide separate secure and non-secure CPU states and memory isolation and I/O isolation with those interrupt controller support. So for those, this is proposed by the ARM, and it has been adopted by the in industry like the Qualcomm's QSEE and Samsung's Knox, and also there's some work like to define this global platform APIs for this third-party developers to develop those trusted applications for this this TrustZone architecture. So our work actually focus on study this the cache on this ARM TrustZone. So for this most of these ARM processors, they have a 2-level of caches. They don't have a 3-level caches. So the level 1 cache and the level 2 cache. So we talk about if we have this like multi-cores, right? So in core 0, for example, in core 0, we can have this level 1 cache is on dedicated for each core. And the level this core 1 have its own level 1 cache. And this cache can be the instruction cache, I cache, or the data cache or D cache. And for the level 2 cache, this is has this unified, means it contains both this data cache and also instruction, all just holding this level 2. They don't distinguish those two types of data. And another thing is there's a NS bit. You can see here in this cache, level 1 cache and level 2 cache. This NS means non-security. So if this is non-security bits, it's this 1 means this is being used by the normal world. And if this cache line is used by the secure world, then it's 0. So we can see here in this level 1 cache, when it's being used by the secure world, all those cache will be marked as 0. Right? It's all just shared by this, occupied by this secure world. But in the level 2 cache, we can see some line, cache line will mark as 1, some one is 0, means this some being used by the normal world, some used by the secure world. And also there's one, this TrustZone TZASC address space controller, which mainly focus on this protection isolation of the RAM memory. And because they have this 2 level of the cache, right, level 1 and level 2, so they define this cacheability domain. The inner cacheability domain is for this level 1 cache, which are exclusively owned by one each core. And also they define this outer cacheability domain, which on this level 2, which is shared by multi-cores. Right? And here ARM allow we just define this cacheability features for each domain. Means for this inner domain, cacheability domain, we can configure this as a non-cacheable, read back, read through, or read allocate. And for this level 2, also we can decide a different set of these attributes. So those are some background on this ARM TrustZone. Now let's introduce our first work, this cache-based rootkit. From this work, actually, is based on, initially, we have one observation. This is the secure world. One thing for the TrustZone is the secure world has a high priority, high privilege. So they can access all the memory on this untrusted domain, the normal domain. But the normal domain cannot access those memories in the secure domain. But here, one thing is on the cache, actually secure world cannot access the CPU cache for the normal world. Remember, actually we have this cache, right? It's NS bit. So here we have this one. So when this secure word access is is cached, it can only access those NS bits equals to zeros cache line. For those NS bits equals 1, they cannot see them. So this is one observation. Another observation is so the cache content means actually there's 2 lines, 1 line occupied by the secure word, 1 line occupied by the non-secure word. Actually, those content may be different, even if they are mapped to the same physical address. So we will see an example later. But based on this observation, we call it the cache incoherence. So we define a new type of rootkit. So what is rootkit? Rootkit actually is they have 2 goals. One is first breaking your system, right? Get access to your system. Another goal is, okay, they want to conceal their presence in the system. So they want to achieve this advanced persistence, right? Keep existing in your system for a long time, being stealthy. So for achieving this rootkit, the stealthy, there's in general 2 directions. One is, okay, we got in a lower position, means the high privilege in this whole software stack. For example, some malware, they just compromise the hypervisor, right? Then this old virtual machine will be just vulnerable, maybe compromised, because this high hypervisor has higher privilege than this virtual machine. And even lower if the attacker can just insert a malicious code into the BIOS firmware. For example, the system management mode, or this Intel AMT. Then the whole, including those hypervisor, virtual machine, those OS are not secure anymore. So this is one direction. Another direction is, okay, there's a number of work, they say manipulate hardware, some hardware features to hide those malicious activity. So it's keep it just you cannot find me. So I just have found a unique way. For example, if they can change this DRAM address mapping table structure, or they just change some ARM registers to redirect the location of exception vectors. There are a number of different ways. So here, this one we just talked about for the system introspection. This one is about, so now we have this TrustZone, right? We mentioned TrustZone has a higher privilege. So they can look into the virtual machine manager, hypervisor, OS, or application, or this memories actually in the non-secure world. So if there's any malicious attacker, they compromise the whole normal world, including the hypervisor. Then we, from this TrustZone, we still can just detect those malicious code by read out that inspect the RAM memory. So this is because for this higher privilege, this each layer you consider TrustZone can look introspect the hypervisor can introspect the OS, and OS can introspect application, right? So, but here, one challenge, you need to fill this semantic gap when you want to understand what happened in this. So, but to defeat this system introspection, even if say now this TrustZone, they deploy some like for malware detection, or this OS integrity checking, those things. So what we can, the threat model is assume the normal OS, like rich OS in the normal world is compromised. But this we see this TrustZone still can be trusted. So we don't have higher privilege, right? We cannot compromise this TrustZone. So, and also we consider this for system introspection, they rely on this acquire this memory and analyze memory, see if there's any suspicious activity. So our just choose a direction to hide those malicious code. So from this introspection. So for this introspection, actually we can see for access the memory, there's generally two directions. One is we read from DMA directly, right? We're just using some network card to directly read this memory address, the space. And another direction is, okay, from the CPU, we just go through this page table, those things, we can access the physical memory. So this one show an example for this secure world and non-secure world, right? Even if they are accessed to the same physical address, right? This 0x1234. So they have this in the cache line. We see there's two cache lines. One is NS equals to 0, belongs to secure world, and 1 equals to the non-secure world. So even if they point to the same physical address, but their content actually could be different. That is because actually they point to different, they can first, for this non-secure world, they can access this data, save the malicious code, those data in the cache, and without write through those data into this physical memory. But when this secure world, they check, they will see a consistent cache and also the physical memory. They are just some normal data. But actually, in this way, we can hide all those malicious code only in the cache. And then even if the secure world wants to do this memory introspection, they want to read out, say, oh, for this physical address, this one, what's the value? They will read out what actually in this physical memory. Here is normal, but actually the malicious code is saved in the cache, which marked for this non-secure world. So based on this idea, we can achieve this incoherent cache. But here one challenge is the cache content is dynamic, right? It will be evicted quickly. So how can we just keep this malicious code in the cache? So we use one technique called cache locking. So ARM processor, they offer this cache locking property. Say, okay, if you just lock some line, some way of data, so then those cache line or cache way will not be evicted. It will always be there. So they design these features actually to improve some performance of like for the real-time system. They want to speed up the processing. So for certain piece of code, they want to say, okay, lock it in the cache. So we will use this more frequently. So they define, so they support this cache locking. And so we use this cache locking to lock our malicious code into this cache lines, which marked for this non-secure world. So after this, see here, this code using this cache locking, we can make sure our malicious code will only appear in this cache, which marked for the non-secure world and will be locked in this cache. So here, now we achieve this two goals. One is in this absence from this RAM. We don't have the malicious code in the RAM. So another thing is how do you load this malicious code into the cache without leave any traces in the memory, right? So we use a technique called cache as RAM. So this is about, okay, think about this BIOS. When BIOS first put up system, the RAM is not enabled first. Actually, the BIOS, they use cache as the RAM. They simulate, using the cache to simulate the RAM to run code, their code directly in the cache. So in this way, we use this cache as RAM. to only load this malicious code only in the cache. So this will not be saved in the RAM. And also we can just use this cache locking to lock this malicious code in the level 2 cache. So then another question is, you can prevent this introspection from the secure world. Then how about this normal world? If this normal world has not been just compromised or been just recovered, so they can just read this memory and also read its own cache. Those cache is marked as a non-secure cache, right? So this normal world can definitely read out this content saved in those non-secure cache. So to solve this problem, so we study this ARM, this physical address space. We just see here, they have some system reserved area in this I/O space. So our idea is we map this cache, our cache, to this I/O space, I/O-based physical memory. So by doing this, so they have some nice property. So for this I/O address, actually usually they should not be read or write or executed for the system. We just do some through our experiment. We figure out. So if this OS just blindly try to read, write, or execute those environments, the system may crash. So we can just so usually this think about this malware analysis or scanning. They will not scan all those I/O addresses. So another thing is we do is for cache. We even you use for this rich OS, they do this cache flashing. Right? They want to flash out the content to memory, but by just mapping this to I/O address, so we can to make sure this those data when the cache data from the cache being flashed out, they will be simply dropped. So we implement our system in this Cortex A8 processors, and we verify, okay, this cache existence, the rootkit. Actually, we just implement this interrupt vector interception. So we intercept this normal interrupt vector table. So we verify this cache, this malicious code existing in cache, and it can be there for a while. And also for this, we can elude those detections from both the normal world and the secure world. So something about this work is when we submit this paper multiple times to this top 4 conference, and always many times reviewers ask one question. So, oh, you can just develop a nice technique to hide, but it's so easy to detect them because you need to have this cache locking, right? And you need to modify the system. So if we know you do those modifications, so we can easily catch your this CacheKit, this rootkit. So what's your contribution? So at the beginning, we just don't know how to answer it, but later we figure out, so there's something called this rootkit paradox. So it's say for all kinds of this rootkit, actually, if you know their fundamental, this basic idea, then all of them can be easily detected, right? So same thing for our work. So then we just explain this in our this paper, and then it's finally being accepted by this Euro S&P. So for some limitation of our work, one is so for persistency, when this system just reboot, right, then our system will be gone because the cache will be totally flashed. So we need to have this for this attacker malicious code to do again to load this malicious code into the cache using the cache as wrap, and then perform all those procedure once again. And also another limitation is for example, for this Samsung Knox, they have developed some technique to enforce this the kernel integrity in the normal world. So it becomes, if you cannot defeat their this real-time protection mechanism, so it's hard to insert our rootkit. So this is the first talk. So before I talk to the second one, is there any questions?
I have a brief question. Is all of this, obviously the TrustZone is specific to ARM, but I'm wondering if there are similar attacks against other trust execution environments, for example, like SGX or.
Yeah, those is unique to this TrustZone. SGX, they don't suffer from this attack.
Is it because of this kind of NS bit weirdness? I'm not an expert on this stuff, so I'm.
Yeah, this you compare this SGX with this TrustZone, is SGX consider more about, we just isolate, we protect the process in this untrusted OS. Right, so their hardware, they using those MEE for encryption and clean cache. They have a better protection on cache than this TrustZone. TrustZone, actually, you think about it, it's just we just separate two environments, and then in each environment you can install hypervisor, OS, everything. But they leave to the user. You need to do a better job to protect the cache. From hardware level, they don't provide, for TrustZone, they don't provide some perfect protection on the cache. Instead, SGX did a much better work. So this attacks mainly for on this happens on those TrustZone, not SGX.
Great, thanks.
Okay.
Do you happen to know whether the new Mac machines, the new ARM-based Macs, are going to have this TrustZone?
You mean the Mac?
Yeah, the ones that the ones that were announced yesterday or whatever it was.
No, usually on the Apple, they use a different solution. They just use a coprocessor. So think about this Touch ID in our MacBook Pro, right? They what behind that is they have a ARM, the small ARM processor. They isolated just from the main application processor. They process all our fingerprint, credit card information in an isolated physical processor. So it's not like TrustZone. TrustZone is like still the same, the one processor, but you support this two states. You can sometimes you run secure application, sometimes you run non-secure application. But for the Apple, their design solution is we totally just use two these separate processors, coprocessor they call. That's why it's based on ARM. This ARM. I talked to some Apple guys. This is ARM series, some, but they don't want to tell me the details.
Okay, no, that's what I was wondering about. Okay.
Okay, great, thank you. So now let me talk about the second word. Second word, this is this year's CCS paper. So we just first let's talk about what is IEE. Okay. So the traditional usage of the TrustZone we see here, they have secure word and non-normal word, also called non-secure word. So they have some limitations for this usage. One is when we install more applications in the secure world, right, the trusted computing base, the TCB, will become larger and larger. And so those manufacturers, those vendors, and also they will just close this secure world after they just have the smartphone on the market. So they don't allow third parties to install their own applications into secure world. So so to solve this problem, so there's some solution called isolated execution environment. The idea is instead of install those sensitive applications in the secure world, how about we just install this in the normal world? And then we use this IEE monitor to protect the whole environment in the normal world. So this idea is pretty similar to the SGX, this solution. SGX is, see, okay, we create one, this called enclave, right, in this OS, and then they use hardware like a reference monitor to enforce, okay, to protect this secure application from this untrusted OS. So here, this one, IE, this, okay, instead of we rely on this pure hardware solution, we use this combine this IE monitor. This is some software, and also we rely on this secure world, which can protect all those monitor. So if this IE monitor can be trusted, can work well, then we can guarantee this secure application can be protected. And for those untrusted applications also running on the normal world, they cannot access to these secure applications. So the benefit is by moving those applications into the normal world, we can reduce the TCP of this trusted world, secure world. And also now this third party can install this freely their application in this IEE environment. So here, for this one, we perform a study, see, okay, then to protect this IEE's data, what should be guaranteed? So one thing is when there's IE is running on one core, there's another core run some untrusted procedure. We need to guarantee this core, even if it's malicious, it cannot read out or access this data running in this secure core 0. So it's including this memory cache registers, which belongs to this core 0, should only be accessed by this core, but not by other this untrusted applications in another core. So another requirement is, so when we run this one in one core, when we finish, because this application just run out of all the time occupy this core. This core, for core 0, it will run this secure application and non-secure application interactively, right? Sometimes for secure application, sometimes for non-secure application. So when this secure application being switched out, we need to protect all those data or states or data or code when it's switch out. And when next time it's turned to be resumed, we need to make sure it's securely load those their data or code. So we need to, in other words, we need to protect this switch in and switch out this process. So when we study this existing number of this IEE work, including 2 NDSS 2019 papers, one is a Sanctuary, one is a Ginseng, and they all propose some IEE solutions, but they all suffer from some this attack. This we call is a catch in the middle. So the idea is for protecting this IE environment in the normal world, they focus more on protecting the IE memory. But for this cache, one thing is this cache now is in the non-secure cache because now this IE running in the normal world. So this will can be accessed by some untrusted application or this untrusted OS. They can write to this cache by mapping to the same physical address. So by doing this, we can just say how this attacker can violate those models. Right? For this core isolation storage, we just figure out by using these shareability features, they can just steal sensitive data from another core. And also we found another attack. One is just totally bypass those secure cleaning process when switch out. Another one is just that we can misuse those some incomplete security measures. So we will see those examples. For the sanctuary, this one, they provide, actually their work is pretty solid. They think about, okay, protect this memory, and also think about when we run this security sensitive application in one core 0. And since this level 2 cache is unified, maybe shared by all these cores, so they will just configure this core as to excluding this level 2 cache, means they don't use. Remember, we have this cacheability domain, right? So they can consider this L1 cache as a write back, write through, but the level 2 cache as non-cacheable. So in this way, they don't need to use level 2 cache. So they can avoid leaking data into this shared level 2 cache. So, but here we just figure out, okay, they miss one critical attribute of this level 1 cache. This is called shareability. So this shareability is to control the synchronization of this level 1 cache. So by default, all these ARM processor, they just enable this shareability attribute. So if you just, for example, for this one, this core 0 is set as shareability, and this is also shareability. Then by reading, when any data change on this core 0, this will be controlled by this Snoop control unit, SCU, automatically synchronize to other core, the cache, level 1 cache. So in this way, for this attacker can eavesdrop, can just the information directly by just setting this shareability attribute. They know, okay, what happened in here. And also by manipulating, writing its own level 1 cache, they can also write to this secure applications level 1 cache. So we just verify this in using our experiment. So another one is for Jensen. This is another NDSS 2019 paper. So this idea, their idea is they save all those sensitive data in the registers. So they can protect these attackers from in this normal world. And also they base on, say, what if we want to switch out? So before they switch out, they need to clean out those sensitive data, right, in the register or in other places. So here, they need to rely on this reference IEE monitor to do this cleanup, since this OS in the normal world cannot be trusted. So they have to make this called domain or word switching. They do this by reading this secure memory, because they are still in this normal world. So they can only access the non-secure memory. So when they access those secure memory, they will generate abortion, interrupt, which will trap into this monitor. And the monitor will clean or encrypt the data, and then get back to the sensitive function, say, okay, now you are safe, you can switch out. And then this core can just run other untrusted procedure. So here, by manipulating this cache, we see here they assume their model they assume, okay, there's nothing in the cache. So we will just have this cache miss, and then we can directly access this secure memory. Then it will trigger this abort. But actually for attackers, if they allocate some data into this non-secure cache. So now this time, this secure application will read this memory, right? They think they read this secure memory, but this will first go through this non-secure cache. Now there is a cache hit, they will directly return, and then they will switch out. So those steps will be totally bypassed. And then those sensitive data in the registers can be read out by those untrusted procedures. So they will save those keys, the encryption keys in these registers. Now they just leaked out all those sensitive data. So for this Trust SAE, this is actually our work in 2015. So this is actually our work. This at that time I still have this single core ARM processor. For those Sanctuary and this Ginseng, they work on all this multi-core system. So at that time, it's 5 years ago, when we developed this system, we just idea is, okay, when this trusted untrusted ritual OS is running, so we just protect all this IEE, this being suspended, and always memory will be encrypted or protected by the hardware features. And when this IEE is running, okay, it can access this non-secure memory, but this ritual OS will be suspended, so it cannot at the same time access to this non-secure memory. So this is because we have only one core, right? One processor. So when we run this IE, we can just suspend this ritual OS. So the same thing here, the cache, at that time, we don't think about how to protect the cache. So now the thing is, when this IE suspended, so we didn't do this clear cache cleaning completely. So this trusted this ritual OS may read out some sensitive data from cache, but this one can be easily fixed by just run this cache flashing, right? Cache invalidation instruction. We can solve this. But also another thing is, so for this, when this ritual OS is running, it can write to this non-secure cache. So they pre-allocate some cache content in this cache. And next round, when this IE is running, they will read out those malicious data directly from cache. And they don't know actually this data is running by itself or by in this ritual OS. So after we study those vulnerabilities, those attacks, we just see, okay, how can we prevent those attacks? So summarize, one thing is we need to protect those secure cache attribute. For example, we need to disable this shareability attribute. We need to set those core as a non-shareable. And also when you switch out this IE applications, you need to clean your data in the cache. And also for all this attack, one requirement is the malicious OS, ritual OS, need to manipulate the page table. So they can map to the same physical address. Then by read write to the same physical address, they can manipulate the cache content. So if from this trusted, the secure world, if we can just interpose all those manipulations on this page table by the ritual OS, then it's possible we can defeat those this cache in the middle attacks. So for this work, we just say, okay, we need to protect both the memory and the cache when designing this IE system. So for previously, most work, they focus on protecting the memory, and they don't have just a complete protection on the cache. So we just point out it's important to protect both. And the summary for, yeah, this is similar things when developing this T and also this IEE system is important to protect the security of the CPU cache. So this is the reference. And that's it. Any questions?